Imagine a small group of hominids 900,000 years ago dragging burning logs to their cave. They weren't planning on preparing some juicy T-bone steaks, or were they? Nor did they ponder on the future of this act on us, growing larger brains many generations later. No, they just wanted warmth at night. What if I told you that one single element quietly supercharged almost everything humans did, turning campfires into furnaces, letters into libraries, and horsepower into megacities? Welcome to the podcast Chemistry Forging Civilizations, where molecules find meaning and chemical reactions shape history. Chemistry, the science of changes in matter, built and changed humankind. This is a chemical story of how man learned to use carbon, the backbone of life, which became the ultimate force multiplier. Our early ancestors gathering burning logs was the first use of sources of energy external to one's own body, as a multiplier of force. Even 1 kilogram of damp wood burning for an hour would release more than twice the energy released by 10 people huddled together. That's not just heat, that's imagination in action, and it paved the way for the start of humanity's energy heist, a millenarian process by which we learned to use energy multipliers, wood, animals, levers, and eventually burning fuels and using them in machines. From the use of wood evolved the use of carbon. Yes, I am talking about carbon, the great force multiplier of human history, the architect of life and the builder of our civilization. Carbon, the element all life is made of, presents itself to man under many different faces: charcoal, soot, coal, graphite, diamond, crude oil. Carbon as man's force multiplier. Carbon was the ultimate man's force multiplier from the 18th century to the last years of the 19th century. At the first stages of the Industrial Revolution, coal initially substituted water wheels as an energy producer. Starting in England, were not for the idea to use coal in the production of energy to move tools and machinery, England would have found itself with no more available spots to set water wheels, pulling the brakes on the Industrial Revolution. In the second half of the 18th century, Watt's steam engine appeared and started to be applied to machinery. Suddenly, instead of artisan guilds, factories started to pop up. Population in the cities increased. Living conditions became appalling with crowding and insufficient services. This is the world that Charles Dickens depicts in his books Oliver Twist, Bleak House, and others. By the late 18th and early 19th century, streets began to be illuminated with coal gas lamps, a dangerous mixture of hydrogen, methane, and carbon monoxide, which was later substituted by arc lamps. Railways moved by the steam engine, powered by coal, made the first revolution in mobility. People that were formerly attached to a limited area and had to move by horsepower or by boat when possible, gradually found their horizons widen. Merchandise could now move faster and in larger quantities. Commerce grew exponentially, and so did a new distribution of wealth that left the landless masses in marginal subsistence conditions. Railways made possible the connection of peoples and contributed to the formation of the United States as a single political entity and European integration. With coal on their side, carbon is the great multiplier of force for humanity. The comparison is staggering. Even humble lignite can garner 600 times more power per kilogram than a strong man in hard labor. Sub-bituminous coal produces 1,200 times more than man, and other types reach 1,700 times more energy. Crude oil has 2,500 times more energy potential than man but in its chemical complexity will be the subject of another video. Carbon, the shape-shifter of the periodic table. Carbon sits proudly at the head of group 4 in the periodic table, with 4 valence electrons in the outermost layer and a Goldilocks electronegativity of 2.55 in the Pauling scale, which means it can combine with a variety of elements on both sides of the table by covalent bonding, meaning sharing electrons. Its external electrons live in one type SES orbital with 2 electrons of opposite spin and 2 type P orbitals, each holding 1 electron, but both have the same spin. It can form hybrid orbitals like sp, sp2 or sp3, which give carbon its incredible versatility. It is like carbon wearing different hats for every occasion. Allotropes are not isotopes. Isotopes differ in nuclear mass, but behave the same chemically because they have the same electronic configuration exactly. Allotropes have the same atomic and electron distributions, but different structural arrangement of atoms and widely different physical properties. Carbon has 3 naturally occurring isotopes, C12 and C13, the stable ones, whose abundance is approximately 99 to 1 in that order, and C14 that decays with a long half-life. Instead, it has many allotropes, some of whom are synthetic. Let's meet the stars among them, graphite and diamond. Graphite is one of the softest materials known. Diamonds are the hardest material in existence. Diamonds are forever, sang Shirley Bassey in the James Bond film of the same name. However, diamonds stopped being a girl's best friend after the appearance of synthetic diamonds, indistinguishable from the natural ones to the eye. But what do you think of the title of this song? Are diamonds forever? Let us know in the comments. Graphite, the greasy genius, helped save England from invasion. Graphite is believed to be one of the very few oldest minerals in the universe. Its structure, a marvel of sp2 hybridization, forming hexagonal graphene layers stacked in an ABA pattern so that each carbon does not have another carbon directly above nor below. The overall structure follows a pattern of layer stacking ABA. The graphene layers are kept together by weak van der Waals forces derived from the quantum fluctuation of the electronic clouds of atoms. Following this stacking of layers, it is easy for a layer to slip over the others, thus conferring graphite with the ductility and somewhat greasy feeling on touch. This also makes it useful for pencils and as a lubricant used extensively in modern industry for extreme applications in extreme and high-tech conditions. Graphite retains its lubricating ability up to 450 degrees Celsius or even much higher for a short time. It is useful for ovens and high-temperature equipment. Temperature stability makes graphite find use in graphite crucibles, used to melt metals at up to 3000 degrees Celsius. As a refractory material, graphite was used in Elizabethan England as an internal lining in the molds of cannonballs, which helped make their surface smoother. Thus, it was possible for the English cannons to fire at a longer distance, diminishing cannon wear, defeating the Spanish Armada Invencible, and contributing to the Navy's strength. Railway joints, conveyor systems, air compressors are all sensitive to dust, so that lubricants that attract dust are substituted for graphite. Even in aerospace, graphite is the lubricant of choice because it can withstand extreme speeds, altitudes, and temperatures. Finally, the valves of brass musical instruments or piano moving parts are also lubricated with graphite. Yes, it helps musical instruments survive the chaos of young prodigies. The sp2 hybridization in graphite means it is using just 3 of its 4 outer electrons for bonding. The spare electron per atom confers graphite with high electrical conductivity. This property, in addition to its inertness at normal conditions, leads to its extensive use in microphones, in early arc lamps, as a pressure sensor, and as an electrode material, among many other applications. In those regular batteries that power your many home remote controllers, the cathode is usually carbon black, a porous elemental carbon product obtained from the incomplete combustion of petroleum products, embedded in something else like manganese dioxide. The structure of carbon black is like that of graphite, with most carbon atoms arranged in hexagonal rings, but without the layered structure. Carbon black is also the material for the anode and the cathode in the Halle-Rolle electrolytic process for the production of aluminum, the method used almost exclusively these days. This is a process similar to smelting, where the carbon of the cathode is converted into CO2. The use of graphite in rechargeable batteries, in particular the lithium-ion batteries powering your phone and electric cars, follows the layered structure of graphite, which permits the intercalation of the lithium ions and its reversible expulsion in the reverse reaction of charge-discharge of the battery. Lithium ions are intercalated in between the graphene layers with a capacity to hold 1 lithium ion for every 6 carbon atoms. Prepare to be amazed. As if all this would not be enough, modern uses of graphite exceed all imagination. We will go back to graphite later in this podcast. Diamonds, are they forever? Following carbon's sp3 hybridization in diamond, the structure is tetrahedral, with each carbon connected to another 4 carbon atoms. Each molecular group is connected to other similar tetrahedra in a crystal structure known as diamond cubic. Diamonds form under the most extreme conditions of pressure and temperature. Now I want you to tell me in the comments, what does this diagram of the different phases of carbon tell you? It shows that at standard temperature and pressure, graphite is the stable form of carbon. The horizontal axis is the temperature axis, expressed in Kelvin degrees. Kelvin is the scale of absolute temperature, whose zero is at minus 273.15 degrees Celsius or minus 459.67 Fahrenheit, the lowest achievable temperature, and its divisions parallel those of the Celsius scale. The vertical axis is the pressure axis, in gigapascal gradation or millions of Pascal, where atmospheric pressure is roughly 101 Pascal. STP, standard temperature and pressure, are outside the scope of the diagram, marked in red. The point marked TP is the carbon triple point, where liquid, gaseous, and solid graphite forms coexist. There is another triple point at much higher pressure, where carbon coexists in liquid, diamond, and graphite forms. So, would you be surprised if I tell you that the stable form of carbon at standard temperature and pressure is graphite? Diamonds are metastable at standard temperature and pressure as they are at room temperature. They undergo transformation into graphite, slowly but surely. So, diamonds are not forever after all. If you're surprised by this fact, let me know in the comments. I will tell you later in the podcast what you can do about it. Diamonds are very rare on Earth, but it has been found to be about 4% in meteorites, usually very tiny diamonds of a few nanometers, a few billionths of a meter. Diamonds are used mainly as gemstones, but find industrial use as abrasives and in cutting instruments. The impact of diamonds on civilization. Diamonds have dazzled us for centuries, symbols of wealth, love, and power. But their legacy is a double-edged sword. From the social point of view, diamonds are and have been a mixed bag for civilization. Beyond jewelry, diamonds are industrial warriors, cutting, grinding, and polishing with unmatched hardness, which was crucial in the building of our industrial age. Industrially, diamonds are prized for their cutting abilities, but socially, they've built empires, sparked fortunes, and fueled conflict. The rise of blood diamonds, mined through violence, exploitation, and war, especially in parts of Africa, is a dark stain on their sparkle. Behind every glittering gem may lie a story of suffering. Some governments have tried to curb this trade, but blood diamonds remain a scourge. A reminder that chemistry isn't just about molecules, it's about morality too. Charcoal and coal, the fuels that forged us. Charcoal was humanity's first gateway to metallurgy. Burned in low oxygen, it gave us the heat to smelt copper, bronze, and iron, launching the age of metal. Without charcoal, metallurgy would probably have to wait many centuries to set off. Its structure, disordered sp² domains, porous and reactive. The ordered A-BA layers of graphene in graphite are here disordered and randomly located, domains with oxygenated surface groups and ash from minerals in the biomass. That porosity makes charcoal a thermodynamic powerhouse, perfect for reducing metal oxides. Its oxidation releases energy more efficiently than many metals, thanks to the favorable Gibbs free energy profile of carbon. Charcoal lit the fire of civilization, literally. Graphite, by contrast, is stable and inert. But why? Both are basically layers of graphene. The ordered structure of graphite resists oxidation, making it ideal for high-temperature crucibles. Charcoal's chaos makes it reactive. Graphite's order makes it resilient. The reaction of oxidation of carbon to CO and/or CO2 is thermodynamically very favorable. In thermodynamic theory, a reaction is favorable if it leads to a decrease in the free energy of Gibbs delta G. Yes, we are getting into thermodynamic explanations now. Hold tight to your chair and tell me what you knew before this podcast. If the reaction is exothermic, releases heat, then the enthalpy change is negative. By the way, did you know what the enthalpy is? The change in enthalpy in a chemical reaction is the sum of the heat needed for or released in the formation of the resultant products minus that of the reactants. The second term on the Gibbs equation is the temperature, in the Kelvin scale, times the change in entropy of the reaction. If there are no changes in phase in the reaction, then the change in entropy is almost zero, since entropy is a measure of the number of microscopic ways to arrange the particles in a system. I think of it as the messy room of my teenage daughter. The more ways there were to throw things around, the larger the entropy she produced. And of course, someone had to invest energy in the form of work to overcome the entropy. Do you have a similar situation at home? The more possible configurations there are, the larger the entropy, so that a change from solid to liquid or to gas brings an increase in entropy and a larger contribution of the negative term T times delta S in the Gibbs equation. The change in the free energy of Gibbs for the oxidation of carbon to CO or CO2 is more negative than that of several metal oxides over a wide range of temperatures. This explains why charcoal is useful for the reduction of copper, iron, and nickel oxides. We see that delta G for the oxidation of carbon to CO becomes very negative with increasing temperature, allowing the reduction of additional metal oxides by carbon. Let me know in the comments, why do you think the slope of the Gibbs free energy for the reaction of CO to CO2 is negative? Let's recap for a few seconds. This explains why charcoal succeeded in antiquity to set off the metallurgic age and why it is useful today. But the question you might be asking, why graphite is so inert that can be used in crucibles and other refractories at high temperatures? The answer lies in the structural difference between the two that cause graphite to have a large barrier to oxidation in the form of a high energy of activation. Defects and pores dominate reactivity, adsorption, catalysis, while order dominates transport, thermal, its electrical conduction, mechanical stiffness. Thus, charcoal, being highly porous with a disordered structure, has an extremely low energy of activation to oxidation. The larger the surface area available for contact between the reactants, the lower the activation energy required to get the reaction started. Charcoal, because of its structure, its porosity to oxygen, has minimum activation energy and the oxidation can proceed. Besides its use in antique furnaces, charcoal was used in the production of antique glass, in cooking, and in inks. But eventually, it was gradually substituted by coal, particularly in areas where the production of charcoal led to deforestation. Charcoal, as graphite much later, had influence in war as well. Chinese powder contained about 15% charcoal, and it continued to be an important component of firearms powder until the end of the 19th century. Today remains a component of powder in fireworks. Coal, not like charcoal, is a fossil fuel that is mainly carbon, but contains small amounts of hydrogen, oxygen, nitrogen, and sulfur. It is a product of plant decay. However, it is a solid found in rocks as a distinct stratum. Depending on the time and conditions of decay, there are several types of coal: lignite, sub-bituminous coal, bituminous coal, or anthracite coal. If you watched our podcast about the chemistry and contribution of paper to civilization, you will recall that plant material is made of lignin, hemicellulose, and cellulose. Peat is the precursor of coal and is made mostly of lignin. Lignite is the lowest rank coal with a 70% carbon content used exclusively as fuel to produce electricity. Anthracite has the highest percentage of carbon per weight, 94%, followed by bituminous coal, 84% carbon, which ranks above subbituminous and lignite. Subbituminous coal is used mainly for steam-generated electricity production. Bituminous coal was the fuel that ignited the Industrial Revolution. It was used to produce the steam that moved ships and locomotives and made the machines possible. Nowadays, it is used in the production of coke and, of course, in the production of electricity through steam. Anthracite coal, which is dense and hard, is mainly used for commercial and household heating. The contribution of coal to forge the civilization we are in ranks second only to crude oil, another carbon mineral produced by the decomposition of tiny marine organisms and vegetal matter over the ages. Carbon dating, time traveling through radiochemistry. C14 is not native to Earth's crust. It is forged in the stratosphere by the bombardment of cosmic rays. high-energy protons and helium nuclei called alpha particles. High-energy neutrons are produced, which bombard nitrogen, the major constituent of air. Its atomic number is 7, neighboring to carbon. The bombardment of nitrogen-14 with neutrons makes it emit one proton, which converts it into carbon-14. C14 enters the biocycle as C14O2, which is incorporated into plants and into the living organisms that eat them. When the living organisms die, the absorption of carbon-14 stops. From then on, the amount of carbon-14 in the residue is an indicator of the time where the living organism died. C14 decays into N14, emitting an electron and an antineutrino with a half-life of 5,730 years. The half-life is the time that takes the radioactive material to lose half of its activity. Decay isn't a synchronized parade, it's a chaotic probabilistic event. At any moment, a neutron in the C14 nucleus may destabilize, releasing a flash of energy and a beta particle as it transmutes into nitrogen. The half-life of C14 is 5,730 years. The decay in radioactivity follows an exponential law. The activity at a time t equals the initial activity times the natural constant A elevated to a negative exponent dependent on the elapsed time. The decay constant lambda is a function of the half-life so that it is different for each radioactive isotope. We calculate the time t, the time elapsed since the death of the sample till present day, from the decay equation. By reading the ratio of what remains n against what was there at the start, n0, we aren't just doing math, we are interrogating the atom. We are forcing the architect to reveal the date of the crime. Carbon-14 is our chemical time machine, dating life from 300 to 50,000 years ago. But it's not perfect. Atmospheric C14 levels fluctuate. Nuclear testing in the 1950s skewed the data. Marine organisms absorb older CO2. So scientists calibrate, correct, and refine, turning chemistry into chronology. Carbon in modern armed conflict and beyond. The amazing chemical story of carbon is not over yet. We now return to graphite. After having helped England become from an insignificant island to a world empire through the Navy, graphite now became the material for the graphite bomb. The graphite bomb is not a regular bomb. It is a non-lethal device used to neutralize power stations and electrical facilities. Remember, we mentioned the sp2 hybridization of carbon in graphite? Remember that carbon in graphite uses just 3 of its 4 outer electrons. Remember that the molecular arrangement on graphite confers it high electrical conductivity. However, if one just drops a cloud of graphite dust over a power station to be neutralized, chances are that nothing will happen. Why is this? What is your opinion? Drop a line in the comments. I want to know what is your idea. Most likely the particles would fall too quickly, dissipate in the wind, and fail to bridge the physical gap between high voltage components. Enter the world of composite materials, and more specifically, carbon-based composites. Composite materials are a vast subject that belongs mostly to materials science, even though we will publish a future video dealing with composites. Subscribe to the channel to get advance notice. Epilogue. Carbon is everywhere, in diamonds and soot, in DNA and diesel. It's the skeleton of life and the fuel of progress. From ancient fires to electric cars, from cannonballs to nuclear reactors to carbon dating, carbon has multiplied our strength, expanded our reach, and shaped our destiny. Carbon is not just an element. It's a story of fire, force, and the future. I owe you the solution of the riddle about diamonds being unstable at room temperature. The rate of transformation is so slow that it is imperceptible. You can be certain that neither you nor your descendants will notice the changes to the naked eye. Further aspects of carbon, like its role as the backbone of life and the immense influence of crude oil, are the subject of other videos. If this journey through carbon sparked your curiosity, hit that like button and subscribe for more chemistry that changed the world.